We'll continue working on this example. We were about to find our function and our first three derivatives at x equal pi over 4. So here we had negative 2 times the sine of 2 times pi over 4. That's negative 2 times the sine of pi over 2. Negative 2 times 1. So the output of the function at pi over 4 is negative 2. Here we have, nope, working too fast. I picked up f prime. So we'll do this down here. This is the cosine of 2 times pi over 4, or the cosine of pi over 2, which is 0. So that tells us that this term will not be in our power series. So we're going to have to definitely generate at least one more term. So we'll go there. All right, now I'm back on track. So the second derivative is negative 4 times the cosine of 2 times pi over 4. We're going to have issues there again. This is negative 4 times 0. That's 0. So we'll have to pick up another term. And then here, the fourth derivative is 8 times the sine of 2 times pi over 4, which is pi over 2. That's 8 times 1. That's 8. So we could come down here, and we know that our power series, the first term in our power series, is going to be this linear term here that has a coefficient of 2. And that gets multiplied by the quantity x minus pi over 4. And then we're going to have the third derivative here. So far we have the first derivative and the third derivative that get involved. So that's plus 8 over 3 factorial times x minus pi over 4 cubed. So I can tell by this pattern that I'm going to need the fifth derivative, and I'm pretty sure I'm going to need the seventh derivative as well. Those, because I think everything, that is even so far has had a coefficient of 0. So let's get some more space here. And the fourth derivative is 16 cosine of 2x. Are we okay if I do that? The derivative of sine is cosine. The derivative of what's inside is 2. So I know that's what that's going to look like. The fifth derivative is going to look like negative 32 sine of 2x. Are we okay with that? The fifth derivative at pi over 4 is negative 32 times the sine of pi over 2, which is 1. So I could add that term here. This is minus a 32 over 5 factorial, right? Because my fourth derivative coefficient would have gone to 0. Anything with cosine in it, I can see that pattern here. Anything that has cosine in it, once I evaluate that at pi over 4, it becomes the cosine of pi over 2, which is 0. So there's the first three non-zero terms. This is going to be a negative 64 cosine of 2x. It has cosine in it. I know that's going to 0. And I'll come down here and do this one. This one will be a positive 128 sine of 2x. And so my seventh derivative at pi over 4 is 128 times the sine of what's going to be pi over 2. So that's a positive 128. This is my seventh derivative, x minus pi over 4 to the 7th power, and plus dot, dot, dot. So just because it says show the first 4 non-zero terms doesn't mean you're not going to have to find higher order derivatives. All right, so keep that in mind. The work that we did for our approximating polynomials is identical to what we're doing here. Once again, we'll show the first 4 non-zero terms. And so we have f prime of x. We're just going to show the things that we know we're going to absolutely have to have. I would rewrite this as 4 minus x to the negative 1/2. Since your numerator is a real number value, using the chain rule is going to be easier than using the quotient rule. So taking the derivative of that in x, the negative 1/2 pops down front. Don't change what's inside. Reduce the power by 1. And then times the derivative of what's inside. So this actually cleans up to be a positive 1/2 times 4 minus x to the negative 3/2. And I'm going to go ahead and clean it up before I take another derivative so it won't get just that much more complicated with all my negatives that are going to show up. So the power pops down front, multiplying negative 3/2 by 1/2. 4 minus x to the negative 5/2 and times the derivative of what's inside. So again, a positive coefficient. And then the next one will be negative 15/8 times the quantity 4 minus x to the negative 7/2 times negative 1 makes it a positive 15/8, 4 minus x to the negative 7/2. All right, we know we are centered where? That tells me I am centered at 0. So I will need f of 0, f prime of 0, f double prime of 0, and f triple prime of 0. So let's plug that in. F of 0 is 4 minus 0 to the negative 1/2. That's 4 to the negative 1/2. That is 1 over the square roots of 4. That is 1/2. The next one is 1/2 times 4 to the negative 3/2. Now, this is where it could get a little complicated and where we could get into some trouble algebraically. So I'm going to tell you that's a perfectly good real number value. This is a perfectly good real number value. If all they've told you to do is build your polynomial, don't spend a whole lot of time trying to clean this up. This cleans up really quite nicely. It's 1 over the square root of 4 cubed, which cleans up to 1/2 times 1 over the square root of 64, 1/2 times 1/8. It cleans up really nicely. But look, I mean, I almost made a mistake right there. But look how much algebra has to be done just to get there. Now, if I had to pick this up and do something else with it, then yes, I would probably take the time to go ahead and clean it up. But a real number is a real number is a real number. Don't spend a whole lot of time doing algebra, cleaning things up when we don't have to. Leave it alone. Just because it's not in its most simplified form doesn't mean it's wrong. Okay, so P of x is f of 0 plus f prime at 0 times x minus 0, yes, plus f double prime at 0 over 2 factorial times x squared plus f triple prime at 0 over 3 factorial times x cubed, and I'm dealing with a series, so it's plus dot dot dot. So just because those coefficients might get kind of involved, don't spend a whole lot of time cleaning things up and simplifying things. All right, let's talk about sums of power series. Because when we talked about series before in all of our series tests, Finding the sums of convergent series was important to us. If we could find the sums, lots of times we were asked to. We knew with geometric series we could, we knew with collapsing series we could, some other types of series we could, but those were the two major ones. So when we talk about the sum of a power series, we want to know what it equals. What is that power series equal to? And so here's the general term of this series, and if we started n equals 0 and we generate all the terms in the series, that's what they're going to look like, and that has a sum. This, remember, is p of x. This is some infinite power series over here. And remember what we said that was true about series versus approximating polynomials? That they were equal to the function that they represented on some interval really close to that center point that it was built around. So here is the sum of your power series. If you want to know the sum of your power series, it's the function it represents. It will be every time. That's pretty powerful stuff. All right, so for instance, if it said find the Maclaurin polynomial that approximates this function at x equals 0, we would go about finding the output of the function at 0, first derivative, second derivative, third derivative, and we would plug it in there. And then we would have p of x equals, and we would have all these terms. We don't have a lot of time, so I'm not going to take time to do it. But we would have all these terms. We'd have numbers in here for these representations. And we would have a power series, and that would equal, on some interval very close to 0, that would equal that function. So the sum of any power series is the function that it represents, that the power series represents. Let's do that instead of it. That the power series represents. Pretty powerful stuff, because now if we want the sum of a power series, we have it. We pretty much start with it. So here, if we're given f of x equals 1 over 1 minus x, and we do all the work and we generate the terms, we can't forget the plus dot 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 in our power series, then we're guaranteed that if this is the true power series with infinitely many terms that represents this function on some interval very close to 0 in this particular case, then that has to be the sum of the power series. Remember, that's what this notation means. That's the sum of the series. That's what that notation means, and of this particular series that we're dealing with. So the sum is the function. The function is the sum of a power series. This, by the way, x to the n, is the general term for this power series. And we'll talk more about that later. So, find the sum of the power series. Here we're given the general term. We're not given the function. We're given the general term. And we're asked to find the sum. In other words, this says find the function whose general term in its power series looks like that. Well, we need to recognize that we're dealing with, when we're dealing with power series, we're dealing with geometric series. Have you noticed that? All of our power series are geometric series. And so if we can recognize A and R, we have a formula for the sum. We'll finish this example in the next video.